Yeah.
Hello. We are the team of polynomials, and today we're going to explain them.
Wait.
First,
What is a polynomial?
you return? Yeah. Okay, first, you check the final behavior to graph them. Here is the table that I'm not going to bother to explain because you have it there. Next, you take the factors, which is P and Q. The factors are the first, the leading coefficient, and the last one, which is the last number of the polynomial. The next step is to divide them.
Now continue.
The next step is to divide them and take out the possible factors, which are the possible real zeros. Next, you check if these zeros are true or false. In the first example, we have that minus 1 is a false zero, which ends up with a residual number of 2. If you plot this number in x, the minus 1, the result will end up in being 2. The next thing you have to do is to check out the next zero. In this case, is 1, which works. With 1 working, we check the square polynomial, which is minus x squared minus 2x. Then you just factorize and end up with the real zeros, which are x is equal to minus 2, x is equal to 0, and x is equal to 1. In this case, all have multiplicity 1. In the case of
what is a multiplicity?
Slow down. In the case of multiplicity 1 or any odd multiplicity, the line will cross the zeros that are already plotted here. And you can plot the graph by using the final behavior and just undulating till you get through all zeros with the rules.
Yes.
Any questions?
What is the multiplicity is even?
Oh, yes. Good question.
Well, that will be our next example. When the multiplicity is 2 is when the final value, which is the real zero, has an exponent 2, either in the parentheses or in the x if the x is alone and no number besides it. For example, here that we have the real zeros that are minus 1 and 2, the multiplicity 1, that is an odd number, represents a crosses, like the example here. And the multiplicity 2, or any even multiplicity, is a bounds.
Can I explain it?
No jalo. Then, the next thing, dude, I don't care if I said it in Spanish. The next thing is to graph it. In this example, we have also the y-intercept. In this case is 4.
Boing.
In the y-intercept, it needs to cross, but it's not a zero, so it will only cross.
Boing.
Like in this example, where it crosses the minus 1, bounces the 2, and ends up with the final behavior in the table below. Now, you know why this is so useful? Any idea?
Hell no.
Well, it is useful because you can graph the time or the development of certain volumes in time-space.
Oh.
These things can even work to calculate the months a baby has inside the mother's belly, like in the example here. It's not accurate, it's just a drawing, but it can also serve like this to doctors to know. It's really helpful.
You're my baby.
For our last example, we can see here a polynomial degree 4 that is way more complicated than degree 3. But the special thing about this is that you need to do the synthetic division twice. Because in the first one you're going to reduce it only 1 degree, making it a cubic polynomial. After this, that we have our first zero, that is 1, we're going to have to do it again and get our second zero, that is minus 2.
Oh.
Then you have to graph it, checking the multiplicity that we already learned and the final behavior. In this case, this special polynomial will have 4 zeros because it's 4 according to its degree. Not always it's gonna have 4 zeros. You can have several fake zeros that are negative square roots.
Wait.
What?
How many are several? Like, do you mean 1,000 zeros?
Zeros.
So zero zeros.
Plural. Let's leave it like that. Plural. Okay, and after you do this, you can graph following the y-intercept and the zeros. Here, the y-intercept is always going to be the number without an x variable or a variable with any letter. In this case, -6 that we see in the graph representation. The graph is going to cross over there.
Oh, so then I can use it to measure radio waves?
Yes. Turns out you do have a brain.
Wow, I have a brain!
Thanks for your attention.